very specific examples of circular motion, okay? And there are the specific examples that involve spooky action at a distance, those field forces, those weird things that are not contact forces, okay? It's not difficult stuff. I don't think you'll find it to be too overwhelming, but there are some little idiosyncrasies and things that that are important to know. So I'm going to start with I debated whether or not to print this out for you, and I decided that I would, and I don't know that I have enough, but maybe I'll share it. We can do it in partners. A little thought experiment. So let me hand it out to you, and then we'll discuss it. You'll have to excuse my clip art choice. I think it was what was available when I was doing this. So. Maybe I'll make the three of you work together. Is that okay? I'll have you guys work in pairs, and I'll give you one for the trio of you. All right. So let me set this up for you and explain what you're trying to do. So I needed a person in the thing, and when I looked on clipart, I found Bart Simpson, and he seemed to be, likable enough. So the situation is that Bart is in a glass elevator. Glass so that we can see what's going on and we can see his expression the whole time. He looks pretty excited the whole time, right? Look at him. Yay, go Bart Simpson. So the game is here, if you look up at the top, it says, for each of the situations below, draw arrows indicating the size and direction of all the forces acting on Bart. Okay? Determine the net force on Bart. Is it 0? Is it positive or negative? You don't need to tell me an actual value, but just indicate to me what that is, and you can set that right in that little thing there. And then the next piece says the strength of Earth's gravitational field. What does that mean? What do I mean when I say the strength of Earth's gravitational field?
Its strength relative to him at his starting point. Strength of
what? That's what of what is my question though.
Oh, his weight.
It's related to weight.
Force.
It's not a force. This is the little. Yeah, it's more like yeah. So let's write this down. Maybe put this in your notes before we go too far. So there's this concept called the gravitational field. And if you recall, and maybe you do and maybe you don't, because I don't remember if I said it or not, that these spooky action at a distance forces, these non-contact forces, are also called
field forces.
Field forces, okay? So these are forces where something, it appears, is pulling, but you can't really see what this thing is. So the gravitational field, it's a construct, friends. We just kind of made it up, okay? It is the thing that affects all masses that are near the surface of the Earth. The Earth has a gravitational field that pulls on everything. It pulls on you, it pulls on me, it pulls on this marker, and this, blueberry and everything, okay? And the field strength is the same regardless of the object. So the gravitational field that this marker feels and the gravitational field that I feel are the same. What is it that's the same? Is it the force that the marker feels and the force that I feel? Are they the same?
No. You feel the same acceleration.
Does that make sense to you? Do we feel the same force? Yes or no? No. The gravitational force, Fg, is equal to mg, isn't it? Yeah, so the gravitational force that the marker feels and the gravitational force that I'm going to feel would only be the same if what? If we have the same masses. And unless this thing is really, really dense, I don't think that we have the same mass. Okay? So those things aren't the same, but the thing that is the same in both cases is the acceleration due to gravity. Okay? So in the case of gravitation, the gravitational field is we'll just say the gravitational acceleration. That's not always true for all fields, but it is true for this one, so we'll go with it. Okay? So when you see that gravitational field thing, that's what it's talking about. So the strength of the acceleration. And then the last thing asks you, now this is kind of hard to see because, my art is so good. He's not just standing like on a carpet square, he's actually standing on a bathroom scale because he decided to take a bathroom scale into the glass elevator with him because he likes physics. Okay? So So what I want you to think about is, what is that bathroom scale going to read as he's riding in this elevator? Okay? I'm going to let you give this a shot for a couple minutes. Have a conversation with your table. Talk about how you can fill this in. And then we'll discuss. Go, go, go. All right. Let's start having a conversation, shall we? Do you guys want to fill stuff out on the board, or should we talk about it as a group?
Actually, Alex,
It sounded really intense. I just wanted to use a whiteboard marker.
Jordan really wants to come up here. Worth having a conversation about. Let's take a look. So the first one. The elevator is standing still. We've got two forces acting. We've got the force of the earth on Bart going down. Everybody agrees with this, yes? And the force of the floor, or the scale, one of the two, on Bart, yes? Everybody agrees with that? Okay, so that's all good. It's standing still. The net force is 0 because he's not what?
Moving. Accelerating.
Not accelerating. The strength of the Earth's gravitational field, they said, is G.
Yeah.
Does that make sense?
Yeah.
Yeah? And the scale reading is equal to the what? Equal to what?
The normal scale reading.
The normal scale reading, like if it was
So 65 times that.
yes.
So equal to the force of gravity?
Yeah.
Is that okay?
Yeah.
I'm going to write that down. Equal to FG. I'm just going to write. That's okay. I'm just trying to keep track here. Okay? When he's moving up with a constant velocity, got the floor on Bart and the earth on Bart that says that the net force is 0. Do you guys agree with that? Yeah. If this elevator was not glass, so if it was completely enclosed, and you were on the elevator instead of Bart, would you have any way to know whether you're moving or not?
No.
So if you're in an elevator, so you can't see outside, right? You're moving at a constant velocity or you're sitting still. Do you know whether you're moving or not?
If it's completely quiet.
Does it
Yeah,
start from that?
very well. It's moving at a constant
Oh,
velocity.
it's a, no.
You're not accelerating, right? Right, yeah. The principle of relativity, you guys have heard of relativity, right?
Yes.
The foundational principle of that whole idea is the fact that if something is moving at a constant speed or is not moving at all, you can't do any experiment to tell the difference. Okay? That is the foundational principle of all of general relativity. Okay? You can't tell. There's no way to know. So we feel like we're not going anywhere. We could be moving at a constant velocity in some other bubble somewhere. We have no idea. There's no experiment we can do to tell between these two.
Like right now.
What's the acceleration due to gravity?
G.
It's still G. Okay? I think what they really meant here was that's like this. Right? Does that make sense?
Yeah.
So I think that this actually goes down here and that is equal to gravity, so those are the same. So again, these two, this first two columns should be exactly the same. Then we get to interesting things. We're accelerating up. So we have two forces, and the sizes of those forces do matter now, don't they? Like the sizes of those arrows?
Yeah.
Which arrows should be bigger?
The force normal. Yeah.
The normal force, or the scale force, right? Pushing up. Does that make sense? This one should be bigger than this one. Why? Because it's accelerating up, right? Tell me about the acceleration due to gravity there. Has the acceleration due to gravity changed? Ellie says no. Why do you say no? His mass hasn't changed, right? Not that that's, yeah. So, and his weight hasn't changed, and the weight is the mass and the acceleration due to gravity. This doesn't change. This is the same. This one is the same. It's the same in all of these cases. Okay? The acceleration due to gravity is the same no matter what. He's not moving like appreciably higher, like up to the mount, the top of some crazy high mountain, right? We're talking about, like going up a few floors or whatever. No, it's going to be the same acceleration due to gravity. If I measure the acceleration due to gravity of my frog up here on the first floor, is it going to be appreciably different? No. Not unless you have some ridiculous way to measure it. No.
forces and everything. Is that what you mean?
Yeah.
Yeah, as I was gonna say,
Yeah.
he's just backwards. Sometimes, you know, he's gotta.
All
All right. So accelerating upwards. What does the scale read? You're accelerating upwards. What is the scale? Where does that readout come from? What does it represent?
The force of Homer on the force of Bart on scale. That. That.
What does it read? I'm still not quite getting it. When you stand on a bathroom scale, right? I'm standing on a bathroom scale. What is it actually measuring?
Force that you apply on the scale.
The force of the earth on me? What's my net force if I'm standing on the scale? 0, right? What two forces are acting on me?
The force of gravity and
The
force
earth and what else?
of
The scale. So really what happens is that the scale is pushing up, or in this case pulling up, okay? And it's measuring how much it's pushing or pulling up. Okay? That's what a bathroom scale does when you stand on it. If you stand on an analog scale like one with the actual dial, okay, it's got a spring in there, okay? And it is measuring the force it's applying to you to keep you from accelerating down through the floor. Does that make sense? That's what a scale measures. The digital scale has a little like resistor in there that changes the current as you step. It's the same process. It's just using electronics instead of springs. Okay? So, is he going to weigh more or less as he accelerates upwards? Is he going to weigh more or less?
He's gonna weigh the same.
It's going to weigh the same amount, but the scale is going to read what? More. It's going to appear as though he's gained weight. Okay? So this thing here is going to be greater than Fg. Does that make sense? Knowing that, tell me about when the elevator is accelerating downwards.
The scale's gonna weigh less.
Right. So if you're having some sort of like body image issue and you really just need to prove to yourself that you weigh less than you do, and I'm not trying to make fun, right? Like, but I'm saying if you want to something, take your bathroom scale, take it into an elevator, start on like a floor up high, hit it, and then watch the scale as you're going downwards, as you're accelerating downwards. Oh my goodness, it's going to look like you lost weight. Did you really lose weight?
No.
No! I don't know where you're coming from, my friend. No!
You didn't lose
but,
mass.
What?
You didn't lose any mass.
Right, exactly. If you didn't lose any mass, you didn't lose any weight. Like, it's not going to change. But the reading will change, right? Just remember that if you're going back up to the higher floor, not to stand on the scale because that's going to be depressing. Because as you're going up, it's going to be like, oh my gosh, you weigh so much more, right? Because the scale is pushing you up more here than it's pushing you up here.
No, we should do this way.
Does that make sense? We have the stuff we could. I don't have time right this second, but we will. So we can weigh less by accelerating downwards. Now, this is the important piece over here. Now he's in free fall. What force did you guys have? What forces did you have in this picture here? I don't know. I'm just asking because you didn't get to do anything before.
Just gravity.
Just gravity, right? Gravity's pulling which way? Down. It's got the force of the earth on Bart. What's the net force? Is it 0? No, it's his acceleration times his mass, right? It's mg. The strength of the gravitational field, has it changed?
No.
No. Now, if he's falling and the glass elevator is falling and the scale is falling, all falling at the same rate, that rate being what?
G.
G, 9.81 downwards, right? What is the scale going to read?
It's going to read as if he was standing still.
No.
So read 0.
It's going to read what?
0.
Why 0, David? Yes, you could.
Because there's no force acting up upon him.
Okay, let's have a conversation. Let's get this, because this is not super hard. Here, let's look over here. Ladies and gentlemen, stay with me. This is an important concept. How many forces are acting on Bart here?
2.
2. The net force adds up to how many? Or how much? 0. The scale reading is really just the force of the scale. Does that make sense? Or the force of the floor? If he's in free fall, is the floor pushing up on him? No. If the floor is not pushing up on him, if the scale's not pushing up on him, what's the scale going to read?
0.
Nothing. As if nobody's standing on it, right? So what is his apparent weight here? 0. Okay? This is his apparent weight of 0. Now, you don't all have one of these, so I want you to take a minute right now in your notes, if you don't have one in front of you, and you don't have to draw the whole thing, but I want you to draw the 2 cases of standing still, this one right here, and the free fall, this one right here. And I want everybody to take a minute and write down 2 or 3 sentences explaining why, when you're in free fall, this is 0. Okay, I'm going to give you just a minute or 2 to do that. If you're not so sure, you can talk to somebody, help each other out. So, here's my question for you. Has Bart's weight changed in any of these scenarios? No. Here he has the same weight that we think he does, or it measures the same. Here he's got more or less. He's heavier than we think. Here he's less. Here he's a lot less, right? What is this called? What is that called if you don't have any weight? That would be like...
0 gravity.
It's not yes and no. It is a case of weightlessness. If you've ever heard of somebody being weightless, that's what we're talking about, okay? Weightlessness is not something magical. It's not something you have to go out into space to experience. To be weightless means that you're accelerating at 9.81 meters per second squared downwards. Do you remember that before we were talking about going over the top of the tornado, right? And if you're small, then maybe your butt comes up off the seat. Let's say you were sitting on a scale instead of on the seat. If we're going up and over that, oh, now you are what? Weightless, just for a moment. Does that make sense? That's all that weightlessness means. So the things that we're going to write that word down because it's important. So to be weightless does not mean that you don't have weight. It means what?
That you measure.
There are 2 pieces. What did you say, V?
You're accelerating down at 9.8 meters.
Yeah, so you're accelerating. I can't spell today. Hold on just a second. At, what'd you say, 9.81? And what else? How are you measuring your weight? What do you use to measure your weight?
Scale.
A scale. What does the scale have to be doing too if you're measuring a 0 weight?
Accelerating downward at 9.1.
Right. Does that make sense? Yeah. So we're going to say, so the object is accelerating downward at 9.81 meters per second, and the scale is accelerating downward at 9.81 meters per second squared. Does that make sense? So the thing about it is there 0 gravity in this situation?
No.
No, is there gravity in this situation? Absolutely, right? As we found, there is certainly gravity acting. In fact, if there wasn't, then he wouldn't be falling. You with me there? Okay? So there is gravity. It's just that everything is falling at the same rate. That's what weightlessness means. Okay? We're going to put that all together in just a minute with one other piece. But before we do that, we get to talk about my favorite physicist and yours, Sir Isaac Newton. You all know how I feel about Isaac Newton, right? If we've been through this a little bit, not my favorite. He's a bad guy. He's smart, or he was smart, but he was not a very good steward of the scientific community. What did Isaac Newton do?
Oh.
He did a lot of things. So you can tell me lots of things. What did Isaac Newton do? Tell me if you can, raise your hand if you can tell me one of them. What?
Discovered gravity.
He discovered gravity! Now, we have to be really careful about this. What does it mean to discover something?
Find
To find it!
Yeah.
So that means that prior to Isaac Newton, what?
No one has
No
observed
gravity.
There was no gravity! How weird is that? Did you know that prior to, like, you know, that time, like, everybody was just floating around? Woo! Then all of a sudden, Isaac Newton's like, gravity! Everything falls. Did he discover gravity, friends?
No.
No. What did he really do?
He made the law of gravity.
Yeah, and he didn't even, Galileo, you've heard of that guy, right? He was born like hundreds of years before Isaac Newton. He did stuff with gravity. What was it that Isaac Newton really did with gravity? Do you know?
The law of gravity?
You should have defined it.
Kind of. He did one very specific thing, and it was an important thing. I'll give him a little bit of credit, but not a lot. He didn't really discover gravity. He did help to explain gravity, I'm going to say, in a universal way. What else did Isaac Newton do? Do you know? He did lots of other important things. What's that?
Motion law.
Motion laws! Yeah! He discovered motion?
Yes.
No.
No, he didn't discover motion. But he did write them down. Here's the sad thing, friends. I mean, when we defined Newton's three laws way back in September, October, whenever that was, it wasn't that hard, right? I mean, they don't take a genius to figure them out. Not that we're not all geniuses, but I mean, let's be honest, we could do it regardless. Okay? He was the one that wrote them down in a nice place. Galileo had done it before him, and many, many people in between had done it as well. But he did write down, and he defined motion in a very succinct way. What else did he do? Yeah! Right? He invented calculus. That he did do. He did discover calculus. Now, we can get all cranky about Mr. Leibniz as well. I don't know if you guys have all heard that story, right? You got Leibniz, you got Newton. They were buddies, but they didn't play nice together. They both discovered, literally, like they actually figured it out. Before Newton, there was not calculus. Before Newton, there was gravity. But there was not calculus. He did discover calculus. We appreciate that. Okay. These two things are important. They're nice. He did a lot of stuff with optics. He did a lot of stuff with thermodynamics. He did a lot of stuff in lots of realms of math and in physics. But the thing we actually do want to talk about today is this explanation of gravity. Okay. That was a big deal. Do you know the story of Isaac Newton?
Yeah.
Have you heard this story? Right? He was at his mom's house. It was like, I don't know, during the plague or something. He had been in like graduate school, and he went home and he was out walking in the gardens, and he was gazing up at the sky. He sat down under a tree, and it happened to be a what kind of tree?
Apple tree.
An apple tree, and the apple fell on his head, and boop, I've got it, right? That's what the story says. Is that really true?
Probably not.
Let's be honest, no, I'm sure it's not. But it is a nice story, I guess, and it does lead us to the way he understands things. And that is going to lead us back to Bart in just a second. So here's what Isaac Newton kind of thought about, or the story goes, okay, that he was observing an apple that fell from a tree. And you can imagine that, can't you? Or a frog falling, for example. I know you haven't seen that before, but here we go. I'll show you right now. Whoa, there it goes, okay? You can imagine that. You can measure the acceleration due to gravity of that, right? So the way that the story kind of goes, right, so he's watching this apple fall, and he was looking up at the sky, maybe it was, close to dusk, and he looks up and he sees the moon. And the question was, is the moon falling? Why does the moon stay in orbit? Is it falling? Is that what's happening? And that's what led us to the thing that Isaac Newton did was to take this idea of falling frogs and falling apples and falling whatevers close to Earth and generalize it to the heavens, quote unquote. Okay? Generalize it to other things, and that was the really big deal. So the question that I'll ask you is the moon falling? Is the moon falling? Jordan?
I don't think so, but if it's... No, never mind that. No.
Yeah.
She's reneging on everything.
Because I was just like, but I think it might be like rotationally accelerating. Actually, I do think that. That is something I think. I think that it has rotational acceleration.
Very la-di-da. Okay. Allison?
I think it's falling, but like in its own sort of like free-fall thing, so that...
In its own sort of way.
I don't know.
I like it.
Falling around like the Earth, but since the Earth is curved, then when it like is falling, then when it curves around the side of the Earth, it never actually hits the Earth.
Okay, that would be sad, wouldn't it? If the Earth or the moon eventually hits the no, that would be. It would have happened a long time ago anyway, right? Like we wouldn't have probably gotten to watch that since, yeah. Jonathan?
The moon is falling, but it's orbiting around the Earth fast enough that it misses that it's always missing.
So you're saying what Allison is saying?
Pretty much.
Okay. All right.
Best way I can think of.
Okay. So let's draw a picture to figure out what in the world Jonathan and Allison were talking about. I'm going to draw a picture of the Earth. You want to do that too? So here's the Earth. And I'm pulling this picture out of the Principia, which was the book that Newton wrote on motion. And on this picture, or in this illustration, we're kind of taking some liberties here. I'm going to draw a mountain on the Earth. Obviously not drawn to scale, but let's just pretend for a moment like it is. Yeah?
Is this the thing we said yesterday where it's like spinning around but it wants to go straight but it's held in
I don't think so.
No. Well, I don't know. I don't know exactly what you're talking about.
with how the moon goes around the Earth and everything? Yeah, with the same with how it
Yes, we're getting there.
Okay.
We're not there yet, but we're getting there. We're just trying to figure out what's going to happen to this thing. Okay. So if we think about this story, so we've got a mountain on the Earth, and instead of just watching the apples fall from the tree, we'll put Newton up on that mountain and we'll have him throw the apples. If he throws the apple with just a direct horizontal velocity, so if we imagine this, so here he is, and here's, I'm just drawing like a much zoomed in picture. There's the tree, and here's Newton with his apple. There's the apple. And he throws it with a horizontal velocity. Tell me the trajectory of the apple. Where's it going to go? Projectile motion, right? No big deal. It's just going to be a little projectile parabola, yes? If he throws it with a little bit more velocity, where's it going to go?
A little farther out to the side.
It's going to go like this, right? So now instead of just throwing apples with your arm, let's get a little apple cannon. Because why not, right? So now I'm going to take that apple cannon up to the top of the mountain, and I'm going to launch an apple with a little bit of gunpowder, it's going to go like this, yes? Eventually it's going to hit the ground because that's what it does. And then I'm going to put a little more ammunition in there. It's going to go a little further. And then I'm going to throw it a little bit harder. And eventually when I throw it harder, it's going to keep falling. But as it's falling, what's happening to the earth?
The Earth's curving away from it.
Stupid earth, always getting in the way, right? So it's just going to keep falling and keep falling. It keeps accelerating towards the earth. The earth is just out of the way, and he better have a little helmet on.
Otherwise
that apple's going to in the back of the head, right? Okay? Now we're assuming a bunch of stuff. We're assuming there's no air resistance. We're assuming that there are no other mountains or buildings or trees or anything. But the idea is there. These things here we would just call projectile motion. These things here we would call projectile motion. But that big one we really call a what? Not so much projectile motion, but a what? An orbit. Yeah. So an orbiting object is really just one that's falling, okay? Around the earth, or whatever it is, around the sun, around Jupiter, around a moon, around whatever, okay? It's falling due to the acceleration of gravity. Which way is gravity pulling it?
towards the center of the Earth.
Towards the center of the Earth. So this is kind of getting at what you were saying, right? If we look at the acceleration here, it's going to be in, so that's a what kind of acceleration? Centripetal. And here it's going to be pulling in, and here it's going to be pulling in. So it is a centripetal acceleration. So that thing is really exhibiting circular motion. It's the same deal. It's exactly what we talked about before. We're just making it on a bigger scale. Okay? Life is okay so far? So now, instead of just talking about an apple, let's talk about something that's a little more interesting to orbit, like maybe a spaceship with an astronaut in it. Okay? So if we imagine that spaceship, let's draw ourselves a little spaceship. It's like art day today in physics class. So if I'm going to draw this spaceship, so here's the spaceship. It's got some little rocket boosters on the back. Something like this, right? And it's a glass spaceship, so I can see in it. If it's sitting on the surface of the Earth, and there's an astronaut in it who's standing on a bathroom scale, okay? What's the bathroom scale going to read?
9 points mg.
It's going to read his weight, right? Or her weight. It's going to read her mass times acceleration due to gravity. Does that make sense? But as that astronaut and that rocket are falling around the Earth, what's the scale going to read? 0. Because they're falling. Okay? What's that? Yeah. Yes, you did, but I don't know what it was. Okay? So weightlessness happens. That's the same deal that is what happens when astronauts are there. Is there gravity
Yes.
when they're orbiting the Earth?
Yes.
Absolutely there is. If there were no gravity, they wouldn't be orbiting. Nothing would be pulling them in. There is certainly gravity pulling them in. That's why they do their orbit. Okay? But they appear to be what?
Weightless.
They appear to be weightless. They appear to have no weight because there is nothing that they can stand on that will push back up on them. Okay? They can do this, so I'm just going to write this down again because it's really important. So the weightlessness idea does not mean that there's no gravity. It just means that they're all falling at the same time, at the same rate. Okay. Have you ever seen a movie that appears to have been shot in space, like maybe Apollo 13 or maybe oh, what was that one that was just on Interstellar, 2001: A Space Odyssey, all of these movies, right, where there's somebody in a rocket ship, right, and they appear to be weightless. Do they do that with strings, right? Are they like flying like Peter Pan?
I think they do that in a pool.
They don't do them in a pool either. Does anybody know how they do them?
When they train astronauts and they put them in a plane and then it like drops straight.
Yeah, do you know what it's called? It's called the Vomit Comet.
Yes, I remember.
It's a really cool plane. If you're ever down in Arizona, they have one at the Air and Space Museum there. So it's this airplane that's like really big, so that they can actually, like manipulate this thing. And basically, what the airplane does is it goes up to a really decent altitude, not really any higher than any other airplane goes. And then the pilot just cuts the engine, it goes down, and it falls, right? And it's falling at about 9.81 meters per second squared, right? Maybe not quite, but pretty darn close. And then they film during that time, and then the pilot pulls back up, right, before they crash. That would be a sad thing. That would not go well. It would be a little expensive, right? So they pull back up, and so they only have like little tiny amounts of time to take a shot, right? Because they're going down, and then they go back up, and they go back down, they go back up, and they only can film when they're going down because they're falling, just like they're falling here. It's the same deal. They don't have to go to space to do this, right? That would be a really expensive movie to make. Okay, we have to go to space now. No, they don't. They are in the atmosphere. Like, there is gravity. There's always gravity, okay? But they're just falling. And everything is falling. Yeah.
Okay. So
I like it when Jordan starts questions with, okay. It's my favorite.
Don't they do some astronaut training like in pools and stuff?
Mhm.
Because it kind of mocks that.
Oh.
Yeah, they do that.
How does that simulate weightlessness? Because is it just like the force of the water coming from every direction makes things fall at the same rate?
So I'm not an expert in astronaut training. I kind of wish that I was, but I'm not. I can say with certainty, right, and you know this because you've all been swimming, that when you're in a pool, you don't weigh as much because there's a buoyant force pushing you up, right? That's why, like, if you're in a pool, you can pick somebody or something up that would be harder to pick up outside of the water. So my guess is that it probably has something to do with that. I don't know much more than that because I don't know what techniques they use.
Okay.
I do also know that one of the things that they will do, you may have seen this on, I don't know, something, like they'll spin them really fast, right, to get them used to very, very high accelerations, right, higher than acceleration due to gravity. So, when they're doing other things. I mean, so there are lots of different techniques that they use because they have to be able to simulate all of the pieces separately somewhere, on the surface.
Yeah.
I don't know about the pool thing though. You can look it up though.
Okay.
I'm sure NASA has a good website that explains all of it. I just haven't looked. Yeah. Are we okay? All right. Okay. We're going to do one more thing today, and then it's going to lead into a couple questions that we're going to do. To do what Isaac Newton did whilst he was at his mother's house avoiding the plague and inventing calculus and inventing gravity. Okay? You will need a calculator, so if you don't have a calculator out now, go get one so that you have one. We're going to jump in and do this.
First, space movies or the Vomit Comet planes?
The Vomit Comet was made to train astronauts and to make movies. I mean, I'm sure that they made space movies that were really, really bad space movies prior.
That they might have, and I remember they might have done that. I was thinking that they might have done really early space stuff.
They may have, I don't know. I am not an expert in that. I kind of wish I was in some ways, but
If you had a really low budget, then a pool might be viable.
I wish. Astronaut training. I know, right? What am I doing? All right. Here we go. So we're going to jump back into Isaac Newton's head. Based on your faces, apparently I have not digressed about Isaac Newton and how much I dislike him, but needless to say, he was not a good guy. He did things like when he figured stuff out, because he figured a lot of good stuff out, like this. Then he wrote in his journal things like, I'm the only one in the world that knows this. La ha ha ha. Maybe he didn't write that. And then he'd like hold out and not publish it for a while because he wanted to like bask in his like brilliance. That just seems kind of rude to me.
Aren't most scientists like that?
No!
But when they make a big discovery like that, don't they like want to be like, yeah, I'm the
But I
best.
thought you would want to publish it faster.
Right, exactly. That's the thing. Yeah, he also, my other little tiny anecdote about Isaac Newton, you guys remember Hooke, right? Like Hooke's Law, like the spring thing. So apparently Robert Hooke and Isaac Newton were enemies. They both lived in, what's that?
I said it makes sense.
I guess, yeah, right. There's a lot of drama in this stuff. So they were apparently working on some thing that was in common, and Isaac Newton was in charge of the Royal Society, which is like the group that published all of the documents in England, scientific stuff in England at the time. He was the one in charge, and Robert Hooke had come up with some idea that Isaac Newton was working on but hadn't made all of the refinements to, and Isaac Newton basically said, yeah, we're not going to take that, and he kicked Robert Hooke out of the Royal Society, and he destroyed all of his papers. And the reason I know this is because I was looking for a picture of Robert Hooke to use for something. There are no, because there were not photographs at the time, right? It was just paintings, and it's not like everybody had a painting of themselves. You had to be pretty fancy, but everybody in the Royal Society had a painting that was done and hung in in that building, and Isaac Newton had that destroyed. Like, he's not a good guy. It just, yeah. But anyway, he did come up with this idea. This whole invention of gravity thing was pretty cool, so we'll give him a little bit of credit for that. Okay, so the question that he was trying to answer was, is the moon falling? And the general conclusion that we've come to so far, at least, is sure, it's falling, right? If it's falling, then the question is, how fast is it falling? Talk to me about the acceleration. The acceleration from the Earth at the place where the moon is. So if we're trying to figure out what that is, we need to make some measurements. What are you going to do? Like get your tape measure out and drop it? I don't know. So let's take some steps here. So the first question that we're going to ask ourselves is, I'm going to call this question 1. There are going to be 3 questions that we ask. Question 1 is, how far will the moon fall in one day? How far will the moon fall, how far will the moon fall in one day? So if I am measuring the frog and I want to know how far it's going to fall in 0.5 seconds, could you do that for me? How would I figure out how far the frog would fall in 0.5 seconds?
Well, you have equations.
You have equations. Get your equation sheet out. Yeah, what equation might you use? Find one. Look for an equation. What equation would you need?
1/2.
Once you found it, check with your neighbors, see if they agree with you.
I know there's no way that's what
All right. Let's make some assumptions. Let's figure it out. So, David, what did you guys say over there? Yeah, you.
The second equation.
I don't know what that is. I don't have it in front of me.
X equals x initial plus v initial times time plus 1/2 at t squared.
And in order to solve, so we're going to solve for x, right? We need to make some assumptions. What assumptions do you want to make? Initial is 0. And so even if it is doing this weird orbit idea that we talked about before, if you think about it, when we started out, we started talking about the frog or the apple moving horizontally. So the velocity in the y direction would be 0 to start out with. Is that okay? And what's that? If you're going to say something, you got to tell me what it is.
You said the moon is thrown from the Earth.
Moon is thrown from the Earth. What about it?
I was just saying the moon was closer to the Earth. It was a joke, but it was not that funny.
I didn't get it. All right, if I want to know x, what else do I need to know? I don't know, I'm looking at an equation.
The acceleration of gravity, like however far it is.
Okay, so let's just say it's g. We don't have any reason to think it's not, right? I don't have any reason to think it's not yet. I've never been up to the highest mountains. Remember, we're talking about like 1600s here. I don't know that g changes. So let's say that it's g. And what else do you need to know?
We have to
Time. Well, what is the time?
put
The time is going to be a day. So let's say that's 24 hours, which, just given our time, I'll tell you is 8.64 times 10 to the 4th seconds. Figure out how far the moon's going to fall in a day. Everybody should do it. Plug it into your calculators. This is not a hard problem, friends. I'll give you a harder problem in just a second, but one thing at a time. Click, click, click. Isabel, did you get a number?
Yeah.
What'd you get?
3.66 times 10 to the 10th meters.
Do you guys agree with her? Yeah? Okay, so let me tell you a secret. Maybe it's not so much a secret. We knew it at the time of Isaac Newton. The distance between the moon and the earth is 3.85 times 10 to the 8th meters. What conclusion does that allow you to draw?
the moon.
The moon would be falling
And it would crash.
like way further, right? Yeah. Yeah. So that would then lead us to the conclusion that Jordan was having in her brain and was unhappy with just a minute ago, which is what?
The gravitational acceleration isn't the same, like in space.
Right. It can't be. Does that make sense? So just to reiterate, if the gravitational acceleration were the same at the location of the moon that it is on the surface of the earth, then the moon would fall a whole lot further towards the earth, crash into the earth, and keep going. Okay? In one day, as compared to where it's sitting right now. That's not happening, right? Because the moon is still there. We see it all the time. Like, it's okay, right? So there's got to be something else going on. So, okay, so we've moved on. We've done question one. We've got to keep going. So we need to figure out something else. So let's figure out then, how far does the moon fall? If it doesn't fall that ridiculous distance, how far does the moon fall? That's question 2.
I thought we were gonna hit the sun eventually. I thought we were gonna collide with the sun.
We're all.
The sun is going to collide with us.
But yeah,
When?
that'll be.
Not for a while. The sun is going to expand and engulf us.
That's a nice.
So
Yeah, so enjoy your next hour and a half.
so it's just expanding. Or it's not
It's going to.
Not enough to matter. The sun will explode first. All right. How far is the moon going to fall? How am I going to figure this out? I can't use the equation that we were using before because I don't know A, right? Any idea how we might figure that out? Let's draw a picture. Here's the Earth. We think the moon is going around in a circle, right? So at some point it's up here. and some point 24 hours later, it's moved to some other place a little further out, like here. Does that make sense? So it's following some sort of circular trajectory. Is that okay? What do we mean, how far would it fall? What does that mean relative to this picture? I don't see any falling happening. What does it mean?
It would be like the change in the solid line from like M1 to E. It would be like the difference between that and the dotted line from the second moon to E.
Wouldn't
Like
it
the
be the
moon a
same,
bit
it
late.
would be the difference between A1 and A2.
Yeah, it was my intention to draw these guys the same because it's moving in a circle. But, so how do
The
we...
arc. Isn't it the arc that moon is falling and what we measure the arc? But that's what, I don't know.
The length of the arc.
Yes, thank you.
Yeah.
Kind of, but okay, so let's go back.
Because if they're equal, then it's, I don't.
Let's go back to my apple. If I'm looking at how far my apple falls, what does that mean? What am I asking in that question? Am I asking how long the arc is? So I know this distance, right?
Yeah.
And at some point when it hits the Earth, I can compare that distance again there, as if, would it ever follow this trajectory, this blue line here?
No.
Only if what wasn't in existence? Gravity. If gravity didn't exist, then that would happen, right? So let's do the same kind of deal. What if gravity didn't exist? Where would the moon go? Straight out, right? Tangentially. Does that make sense? Okay, it's like when Emily gets the scissors out, she cuts off gravity. Right, so now the moon's going to go out to here somewhere. And this here is the distance that the moon falls. Does that make sense? Okay. We'll talk about the approach here real quick. If I look at this, and I look at this, and I look at this, what have I made here? A right triangle? Okay? I know the distance between the moon and the Earth. I told you that a minute ago. It's right there, that 3.85 times 10 to the 8th. I want to know that little delta x. How am I going to find that little delta x? Use the Pythagorean theorem. With what? I know this one, right? This is a right angle. So if I'm going to use the Pythagorean theorem, I need to know how many legs. 2 of them. Can I figure out what this distance is?
Yeah.
How? What's that?
If you know the velocity.
Oh. And that velocity is just the velocity of the moon, right? Like the tangential velocity? Oh, it all fits together, right? So if I know the velocity, so if Emily turns off gravity, and so now the moon is just going to go in a straight line for 24 hours, can we figure out how far it would travel?
Yeah.
Yeah. We can find that distance. I'm going to call this distance, I'm just going to call that D. We know that that distance is going to be equal to the velocity, the tangential velocity times the 24-hour time. Does that make sense? Is that okay? So we need to figure out this one. But like Chris was saying, if we know this and we know this, we can figure out the big yellow line. And do you know this part of the yellow line?
Yeah.
It's the same as that one, right? So you can find the little guy. Okay? I think maybe you need a little bit more information, like maybe you need to also know the period of the moon. Do you know how long it takes the moon to go around the sun, or the moon to go around the earth? Anybody? Anybody? How long is it? Oh, this is an interesting question. Yay! We're learning all kinds of good information today.
31 days.
You're close. 28 days. Which, I'll do the conversion for you, you're welcome, is 2.42 times 10 to the 6th seconds. We have a plan. I want to know what delta x is. I want to know how far the moon falls. I'm going to give you a few minutes to work on that. Go. What did you get for the velocity?
It's more challenging.
Wait.
What'd you get? 999 stuff?
6 meters per second.
Okay. From that, what did you get for this little d here? The distance that it would go if it didn't fall.
I got 8.64 times 10 to the 7th.
You guys want to corroborate that? Do you agree? Is that okay?
And then you do the Pythagorean theorem.
Uh-huh.
So then you square that, add that to 3.85 times 10 to the 8th
Squared. Yep.
And then you get your answer, and then you square root
Square
it.
root that mess.
Yeah.
And you get the hypotenuse.
Yeah, which I got is 3.95 times 10 to the 8th. If everyone else got that, then
Okay, what did you say?
3.95 times 10 to the 8th.
Okay, let me pause that for a second, make sure we're okay. And so that is pretty darn close to this, right? Like, which kind of makes sense. Those should be about like on the same order of magnitude.
Then I think the part that
So then delta x is just going to subtract that.
yeah, which I did. It's you subtract that from 3.85.
Well, 3.95 minus 3.85.
Yeah.
Uh-huh. So how far does it fall?
Times 10 to the 8th, and I got 9.57 times 10 to the 6th.
Okay.
But they didn't get that.
Is it okay? Is it to the 4th or to the 7th?
No.
8.64.
8.64 to the.
That's the 6.
I have 4 written down.
What?
For what? For this one? That should be to the 7th.
Okay.
What?
So is everybody okay with this delta x here? So now we know that this is how far the moon falls. And if you know this is how far the moon falls, then I'm going to just scroll up here for a moment. Use this information or this approach that we used earlier to figure out what the acceleration actually is.
That's just to the 4th, right?
That one says to the 4th, yeah.
They're different.
Yeah, because you're multiplying it by 1,000.
9.58 to 10 to the 6th.
Oh, okay. It used to differently than I did.
Does that make sense?
Yeah, I broke it up though. I didn't. I see. Yeah.
Okay.
Okay. Yeah.
So question 3 is, what is G at the moon? Have you figured that out already? Yes. What is the acceleration due to gravity from the Earth at the moon? So now you know how far it's falling and you know how long, right? Because it's going to fall that far in 24 hours. I want to know what A is. Do it. I believe in you. I think you can. So this is just a projectile motion problem again, right? We're saying the initial velocity in the y direction, or in that falling direction, is 0. So we're just going to solve for A. Does that make sense?
Yeah. And the D is
The delta x. Because this is how far it falls and in 24 hours. Yeah. And the acceleration due to gravity at the location of the moon is larger or smaller or the same? Smaller by quite a bit, right? Allison, did you guys get a number back there?
2.56 times 10 to the negative third.
Say it again, 2 point
56 times 10 to the negative third.
units are
meters per second.
meters per.
Second squared.
There you go. Okay. Hold on to this. Make sure you bring it back on Monday. I'll see you then. Have a good day and a good weekend.